In our previous class, we talked about the elementary kinematic properties of fluid, and we considered the following: shear, curvature, confluence, and stretching. We also discussed about the following properties and their natural coordinates, how we can use their natural coordinates to create a definition of those quantities. And as you can see on the table here, we had that vorticity is a measure of local spinning motion of a fluid, and we saw that vorticity was an algebraic sum of the shear and the curvature. Today we shall be looking at how we can derive a mathematical expression for vorticity and how we can also use that expression to solve the following problem. Let's get started. The first question said, show that the vorticity distribution of a spinning body is given by vorticity equals to 2 omega, where omega is the rate of spin of fluid. So we are going to derive this expression here, vorticity equals to 2 omega. But before I continue, I want us to look at this picture. By definition, we had learned that vorticity is a measure of local spinning motion of a fluid. And if you look at this fluid here, it shows the spinning motion of the fluid. And if we look at this, you can see that the rotating fluid has velocity and it also has a radius. Okay, so let's look at the question again. Show that the vorticity distribution of a spinning body is given by vorticity equals to 2 omega. We can recall that vorticity is equal to the sum of the shear and the curvature. Sum of the shear and the curvature. I hope you remember. But we know that the shear from the coordinates, the shear equals to minus dv all over the n, minus dv all over the n. So we have that dv over the n here means the rate of change of velocity, in the transverse direction of flow. And this is the same thing as we now have dv over the r. Since we are considering a rotating or a spinning body, so we had to convert this to r, where the r here signifies radius. So I call this equation 1. So this is for the shear, and the curvature C equals to V d psi over d. S will be psi all over the S. Okay, so since we are also considering a rotating body, we'll replace V here, and the psi here has to do with angle. So we are going to replace this with 2 pi all over. Then we come here, the ds here. Since we are considering a rotating circle, we are going to put 2 pi r here. We call this equation 2. We can now see here from equation 2 that we have some common terms like 2 pi. So this will strike off this other one. So we are left with V over R for this. And this one can as well strike this. So we are left with V over R as well. Okay. Don't forget that vorticity equals to the sum of shear and the curvature. So we had defined it in that nature. So we'll simply say that vorticity equals to, in place of the shear, we are going to put V over R. And in place of the curvature, we are going to put V over R. So if we decide to add V over R plus V over R, we will have the vorticity equals to 2V all over R. I call this equation 3. So this is another way we can define vorticity. Now, let me write it here. Vorticity equals to 2V over R, where V here is the rotation, the velocity of the rotating body, and R here is the radius of the body or the fluid. Okay, so now recall that V equals to R omega. If we make omega the subject, we will now have that omega equals to V over R. All right, so we have V over R here. So in place of V over R, we are going to replace omega. So the expression for vorticity now becomes vorticity equals to 2, in place of V over R, we put omega. So this is another way we can define vorticity. We can also define vorticity as 2V over R. So these two mathematical expressions represent vorticity. Okay, so we have derived the expression. So let's look at how we can solve the second problem that we had in our notes. So the second question says, if wind rotates as a solid body about the center of low pressure system, and the tangential velocity is 10 meters per second at a radius of 300 kilometers. Find the relative vorticity. But we know that vorticity is defined as (2v) all over r. Okay. From the equation here, we have our velocity to be equals to 10 meters per second, 10 meters per second, and radius is equals to 300 kilometers. The kilo here means 1,000. So use 1,000 to multiply with 300. So we can also write it as 300,000 meters. 300,000 meters. Okay. 300,000 meters. All right. So if we substitute V and R into our expression here, we will have the vorticity to be equals to 2 times the velocity, which is 10, divided by 300,000, divided by 300,000. Okay, so this would give us the value 6.6. After simplifying it, 6.67 times 10 to the power minus 5 per second. Okay, so that is how far we can go. Thank you very much for watching. And I know you enjoyed the video. Please, I would like you to go to the subscribe button and click on it. If possible, like and share to others